Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do on a manufacturing simulation, and in this particular manufacturing simulation we are going to do a sheet metal bending. So right now on my screen what you see, there is a sheet metal 1 millimeter thick which we bended by 90 degree, and we use all elastoplastic material, and this is what actually we are going to do it. So typically sheet metal bending, there are a lot of things people consider is a bending allowance, bending angle, spring back, bending radius, how much force is required to bend this part, whether it goes into full plasticity whole part, or there is some region which is not in plasticity which can get a spring back, and all those. So that's what actually we are going to do. I'll just show you one more time how it looks. I'll just take out the punch and die. So then we'll just have how it looks. So this is a plate bending. We are getting more than 400. 400 is the yield. We are going to use 380x steel grade here, and then you see, okay, then the plasticity is reaching quite a bit area. Then still there is some part which is inelastic, which may get a spring back, and this spring back is typically sheet metal manufacturing bending people, they use 2 to 4%. So before going into doing this, just I'll show you the quick video. There are a lot of analogy techniques are so on my screen what you see is against the neutral axis, the top portion is in compression, bottom portion is bending, and then you see this bending process. So this is in compression, this is in tension, there is a plasticity zone, and then you do a lot of this calculation. So this is sheet metal bending, 90-degree bend operation, different things we are going to do, bend allowance and all, bend angle, bend radius, and then spring back. So I'll just quickly go to the PowerPoint presentation just to start with. So today's topic, sheet metal bending. We are going to do a manufacturing simulation. So sheet metal bending, there are a lot of things, terminology involved. If you do googling, you will find a lot of things. What is a bend allowance before bending? What is a flat area length should be? What should be the plasticity zone, plastic zone length, bend angle, bend radius, a neutral axis, how the stresses are there, how much area is into the full plasticity zone, so there is a little bit of spring back, how much is a bending force required. So if you do googling, you will get all this information. There are a lot of package available which do this calculation for you, but if you can use Abaqus standard, it is just straightforward. You can get all insight in this particular manufacturing simulation. You can get into plasticity zone, a lot of information you can get when you do this. So just to start with the problem, now if you look this problem, the sheet metal is most of the time it is a 1 millimeter or less than 1 millimeter. Width is quite a bit high compared to the thickness. So if you want to do this type of problem, which particular solver we are going to use? We are going to use an implicit solver. If you use an explicit solver for these particular things, you need to make sure when you use explicit, it will be a quasi-static simulation. Quasi-static simulation means there is no inertia effect, so there is a little bit of kinetic energy. So it's better, safe to do this type of simulation using a Abaqus implicit or Abaqus standard. So that way you don't have to worry whether the simulation is a quasi-static, whereas there is a minimum of amount of kinetic energy. Once you use implicit solver, Abaqus standard, there is no inertia effect, there is no density, so you don't have to worry about this. Now the challenges for this type of problem is because it is just supported on a die, then punch is moving, so there is quite a bit of a rigid body mode you can get with this type of problem. So you have to be very careful when you solve this problem. You need to simplify this problem. Now one way you can simplify this problem is you have a thickness and then you have quite a bit width. So this is a clear cut is a problem of a plane strain problem. Now in plane strain problem, when the length is quite high compared to the cross section area, so something like if you consider as a pipe, so you have some cross-sectional area which is minimized compared to this length, then you know the strain in the third direction is a constant. So this type of problem you can consider as a plane strain problem, similar like what you see is a water dam. So the third dimension is such a big, so the strain in the third direction is a constant, so it's a plane strain problem. So we can convert this problem into a plane strain problem. So first we'll look into problem. We decided we'll use a solver like a Abaqus standard. So Abaqus implicit will be a solver we'll use. We'll convert this problem to 2D using a plane strain approach. For plane strain approach, we are going to use a CPE4R. So it's a 4-noded bilinear plane strain element, quadrilateral element with R is for reduced integration and hourless control, but we don't have to worry about reduced integration. We are going to do in Abaqus standard or implicit. For this particular problem, we have 3 DOF, X and Y translation and the Z rotation. So 1, 2 and then you have 6. For getting one of the rigid body mode, we can simplify this problem. This is X-axis, so we can use the X-axis symmetry on workpiece or the plate, bending plate. So that way, once you use that symmetry, we can have control one rigid body mode, that is the X translation, and then since we are translating this X, it will also take care of a rotation about Z. So X translation and Z rotation we can take care once we use a symmetry problem, take a symmetry. So this is what actually guys you have to look. Whenever you look into problem, you start analyze it, how you can simplify it, how you can take care of symmetry. Then for vertical rigid body mode, we have support, but over a continuous loading the plate is going to bend. Then we have to use something like a contact damping between these two contact surfaces, so that way you can stabilize the contact. You can also use automatic stabilization with minimum stabilization energy, and then we can solve this problem. So material is a 380x 1 millimeter thing. The flat length is now 130 millimeter. We are going to use a steel 210 power 03. Then the other plasticity is 400 is yield. Then you see the plasticity data here. So we'll start with this, and the unit which we are going to use is a ton, millimeter, Newton and second. So that's what actually we'll do. So let's start it. I'll just say new. I'll also select a directory, sheet metal bending. So I'll just set a directory. So we'll create first workpiece. We'll say plate, (2D) deformable shell. So 200 is fine. We'll quickly put 0, 0. So that is a reference. Then 65, 0, minus 65, 0, 65, minus 1. So you get a point there. Then minus 65, minus 1. So you get a point here. So we quickly create so you created a plate. So done. So you create a plate. Now we'll quickly split in center, so that will be easy for us to put a symmetry boundary condition. So we'll create a we'll go here, principal plane. We'll create one datum. So it's a YZ, and I'll say create. So it is created there. Now with this datum, it is there. So I can quickly cut it. So you select, create, done. So using a datum, I cut the plate. Now I'll quickly create a metal property, which is a steel 380x grade. You require elasticity, so 210 e power 03 0.3 will create a plasticity data. So 400 is yield. For 400 0 plasticity. Then you have 420. For 420 it is 2% strain. Then you have 500, for that it is a 20% strain. And then you have 600 MPa yield stress, and that for that is a 50% plasticity. You have to now this is a plane strain problem, so you have to be careful. It looks like a 2D, but it is actually 3D problem. So solid, you have to select homogenize. Okay, then now we'll just assign it quickly. So we'll assign it. Done. So assign. So once you assign it, change the color. So you assign that. Now we quickly create second part, which is a die. So this will be a rigid thing. Die will be rigid. So you have different option now. We'll put you have discrete rigid or analytical rigid. My preference is discrete rigid, since you can mesh it, so you can have control on the contact. So it's better to have a discrete rigid. So discrete rigid, approximate side 250. So we'll again create 0, 0 center will create. So 125, 0 and minus 125, 0. So if I fit it, so it's at extreme edge, then I'll create one more point, 0, minus 50. So I get a bottom point, then 50, 0, I get that, minus 50, 0, I get this point. So I'll just quickly create a line. So we have created that. We'll quickly create a fillet. Fillet will be 5 between this and this, this and this, and then we'll create one more center fillet in center, which will be 15. So done. You are done with the die. Now die is rigid. So then you create punch, which is again discrete rigid. And then you create center 0, 0. Then you create 49, 50, and then minus 49, 50. So you've done that. Let's create a fillet here. So you created fillet. Done. So let's quickly assemble it instance. So we created this. So we created the instance. Now we'll quickly position it. So we'll first translate die 0, minus 1. So y direction, I just bring 1 millimeter down, so it is come down. We say okay. Then other position will bring this. Done. We'll just through points will bring it. So you got the position. Now I'll just quickly go back. One more important thing we forgot for the property. The punch we are done, but we are not assigned the reference point. So in the center I'll just assign the reference point. Then similarly for die also I'll assign a reference point. This is good for putting a boundary condition there. So we have done this. So we'll quickly mesh the part. So part wise we'll first put plate, and then global size we'll use a 0.3 millimeter. quickly mesh it. So you can see at least 3 element is there across the thickness. So it's good to capture the bending behavior, its whole bending behavior. So make sure guys you have a 3 element across the thickness so you can capture the bending behavior. We'll assign a material type. So we'll assign, actually by default it is a plane stress, so you put a plane strain there and you say okay, then the material is assigned for this plane strain. Now we'll quickly mesh a die also. Will put up quite a bit refined mesh, so that way actually we'll have a good contact area. So we'll mesh that also. We'll mesh the punch for again 0.3, apply and then mesh it. So all meshing part is done. Now we'll go to the interaction. We'll create the interaction property. So we'll create friction between this die and plate and punch and plate around 0.1. So penalty is 0.1 friction we put. Now the one of the learning for doing this exercise is you can use contact control. You can put automatic stabilization factor, some low factor you can put it. Then we can, for contact we need a surface. So plate will create a surface. So the top surface, then you create a bottom surface. Then we'll create symmetry geometry. So we'll just select that edge. So the nodes on that particular edge will constrain. Now we'll quickly create die. This will be the master surface. Now you select one, then you select shift and then you can select done. Now this particular, once you select 1D like a line things, it asks the two things: choose the side of the edge. So for the workpiece as top, so magenta will be the surface we want. We don't want a yellow surface, so we want a top surface, so we'll select magenta. Then we'll select for the punch surface. So done. Now we'll select yellow. We want the outer surface. So you select yellow. Now we have surface. We'll quickly create the interactions. So the first, it will be surface to surface standard. So it will be die, plate, it will be workpiece. So master surface will be the die. Done. Friction is connected. Now contact control, which we are defined, damping, contact damping, which we are connecting there. Now I will create one more. Punch, plate. So we'll select punch as a master. Then you select top, then you select contact control. So guys, we are done. All contact definition between the surface. So now we'll create some boundary conditions. So we'll go to loads. We'll first create so it will be die, which will be fixed. So select the XY translation, all this Z rotation, then you create for a punch. Punch will be, it's free to move in Y direction. Then you create one more for symmetry X. You can give symmetry X by constraining the X translation and the Z rotation, or you can use a symmetry option here. So we done that. We'll select the set geometry and then we'll say X symmetry. So that way it is constrained. Now we'll quickly create a step, and then the displacement what we are going to give is a 43.8 millimeter. So it will create a bend shape here, and then we'll measure what is the reaction force. So that way we can decide what type of punch tonnage is required to get this part bent, and then get into a spring back calculation. Then we can use that. So steps will create sheet metal bending. It will be Abaqus general, NL jump on. You have to start with very low initial increment, and then minimum increment you keep 1 e power 02, because there will be a lot of contact issue, convergence issue. So start with minimum increment, initial increment 1 e power 03, and then minimum increment you keep it that, and then put 1,000 number of increment. It may get more than 100. NL jump on. Also the one of the thing what we mentioned is automatic stabilization. You put specified damping energy, you use put whatever is their default 0.002% of stabilization energy. And then one of the important thing is, once you use all this automatic stabilization, you have to cross check how much is the stabilization energy generated in the model. So I'll again go to the load. I'll just create one more is for a punch movement. The reason I created a step, because then this punch movement will be the inside step. So I'll give a displacement, and then you select that and give Z minus 43.8. So we have done that. So let's create a job. Metal bending. Let's go for data check. It's fine, you get a message, data check is done. So let's submit and wait for results. So we have submitted the run, we'll just wait for a result. So guys, results are ready. So right now on my screen you can see that it's bending. So let me get into visualization. Free edge, I'll just do it, so that way we can quite a bit check it. So this is what actually you see 2D. You can see the area is getting into plasticity, and then whole area get plasticity. So plate get bent, it gets some area in plasticity, then whole red area, then you see some small portion, you start pushing it, and then it goes into plasticity. So now you want to, if you want to visualize this in 3D, it is very straightforward. You go here, you can extrude element depth wise, so it's a 50. Extrude analytical surface also specified by 50. So you can visualize it how it's bending. So right now it looks like okay, plasticity zone has gone. There are some area which is in elastic region which may get a spring back, but then spring back 2 to 4% is okay. So once you take out this piece and keep it open, it may just spring back. So that is a different topic, we can touch that topic sometime on spring back. We'll just quickly check one more thing is, we'll check what is the reaction force. So if I plot it now, reaction force, so I'll just go to the last end and then I'll just plot reaction force. So reaction force for punch, it's almost like a 956 kilonewton. So you required that much tonnage to really get this part bent. So that is the information you get it out of this. So you get around 956. So the main objective is how to do this type of manufacturing simulation. I hope this will be helpful for you. You can convert this type of problem into 2D problem. You can use automatic stabilization, contact controls, and then you can solve this problem. So thanks a lot for watching this video, guys. Please like us. Also don't forget to subscribe us. This is a non-profit project. We want to take it forward. We need your support to take it forward. So